I didn't put the list of co-authors because it would have gone on forever. This is a lot of work done by a lot of people, but I do want to particularly mention Shen Elipo and Miguel Ángel Morales Maqueda, who did a lot of the work involved in the wave array, which is what the first part of this talk is going to be about. Wrong way. Right. All of this is about ocean dynamics. I am totally ignoring anything to do with land motion and geoid changes. So in the terminology of this Gregory et al. Paper, no gravity rotation deformation effects are considered. And I thought it worth making this point, actually. This is a paper that I was complicit in. I agree with most of it. But it did a good job of defining terminology for sea level, which is something that did need doing, but it didn't touch the sides when it comes to bottom pressure. And there is a whole big issue here about proper terminology for bottom pressure. So I'm going to start with some in situ measurements, and I'm going to tell you the answers because I've got far too many slides and I might not get there. In situ measurements, the bottom line is we can get independent measurements of dynamic pressure differences down the continental slope using bottom current and density measurements at the level of a few millimeters. For oceanographers, this is brilliant from the point of view of correcting instrumental drift, joining together very long time series, and removing the nasty seafloor motion. For geophysicists, the opposite way around, of course. We can use the density and currents to work out the dynamic part, which leaves us with the vertical land motion that the bottom pressure recorders can tell us. The second part, I'm going to put this into a broader context with some ocean model results. And the bottom line of that is that, as we've already heard, bottom pressure, dynamic bottom pressure, this bit that I'm talking about, is much quieter than sea level. Even more true in the tropics and the continental slope than elsewhere. And in those regions, these changes are coherent over very large distances. Oceanographers like this, we can learn about the global ocean circulation. Most things that you measure in the ocean tell you about what's happening there, or within a few kilometers, maybe 100 kilometers if you're lucky. This is telling you about what's happening across the entire scale of the ocean basins. That's really powerful. Yeah?
Would it be appropriate to clarify that the geostrophic relationship that I was talking about is a static, no time evolution built into it, and what you're calling the dynamic pressure variations are ones that intrinsically have to have some ageostrophic to make them evolve.
Yes. So although I'm sticking with geostrophy pretty much, nothing much would happen in terms of time evolution if it weren't for those small other terms which are in there.
But Chris, just one more question about your terminology of dynamic pressure. You're not talking about like in a Bernoulli function, the kinetic energy.
No, absolutely not. No. Right. So oceanographers like it. Geophysicists, again, this coherence along the slope is something that can be exploited for removing that nasty ocean signal. So, hiding the nasty, messy real world. This is the wave array on the Scotian slopes. We put out a series of 6 instruments with bottom pressure recorders and ADCPs to measure the currents. These are short range current meters. They measure the currents in about 50 to 100 meters away from the bottom. And then these plus signs, ignore the tall mooring there. We're focusing here on these little ones almost at the bottom, which measure the density, temperature, and salinity. These are steps about every 600 meters down the slope. It's quite a steep slope, about 1 in 20. That's quite steep. You can get dramatically steeper in some places. But you can also get a lot less steep, even on continental slopes. And you see it suddenly drops to quite a lot less steep as you reach the foot of the slope. So what are we trying to do with this array? We're trying to calculate pressure differences between 2 points down the slope. So we're aiming at d by dz of bottom pressure, dD. That's difference divided by delta z. We use hydrostatic balance in the vertical, take the difference between these two pressures. That's rho g dz. Rho is the density. And the difference between these two, we use that geostrophic relationship that Randy was talking about. We get rho f v, v is the flow into the screen, dx. And we can relate the x and dz with the slope. Instead of dx, we have slope times dz. If you put those two together, we get the p2 minus p1 divided by dz, which appears in both of them. We get this really simple formula. If you know the density and the velocity, f is Coriolis, s is the slope, those are external parameters, then you get a way to step down from one point on the slope to another, get the bottom pressure differences. So here's the data. These are the actual bottom pressures. With the usual drift curling at the beginning. Third one had something weird going on. Every now and then it just jumped and started its drift again. But if you take out those drifts, you get this. Huge coherence in the vertical. That's this. So I apologize for this. Randy calls them mode 1 and mode 2. I call them mode 0 and mode 1. This is mode 0 because there are no nodes. It's basically a large-scale Kelvin wave type mode up against the slope. So if you take the differences now, and I'm going to subtract each one of those from the top one, from RS1, we get this. Totally different picture, totally different spectrum, much smaller. The scale has halved on that. And smoother, but still with vertical coherence. Quite a lot of vertical coherence.
Which one is the shallow, which was the deep?
They're the right way. Top's at the top.
That's the pressure differences between.
Yeah. Yeah, so this is RSN minus RS1. So that's the directly measured ones. Now we try and reconstruct them. And the grey lines are what were on the previous slide. The thin black lines are this reconstruction using the currents and the densities. You can see there is still something dodgy going on right at the beginning. Even though we've done our best to remove the drift, there's something still going on there. And all our ADCPs decided to stop working after 9 months. But apart from that, it worked really nicely. So if you take the differences now, so with differences of differences, the difference between the two ways of measuring those differences, this is what we get. Standard deviation of 1.63 millimeters for RS2 minus RS1, so that's nearly 600 meter step. Going up to, now we have 2,300 meters difference between RS5 and RS1. We're still 4.7 millimeters of agreement, which I was absolutely stunned by. Things don't work that well in ocean dynamics. So that's extremely powerful, I think. We have some advantages. We have a nice monotonic slope. We chose a nice monotonic slope. And we don't have much curvature in the slope, so that is relevant too. this is worth a look at as well. So this is the same thing in spectral space. It's the coherence between those two curves, directly measured and reconstructed. So that the black line is that. Periods shorter than about 10 days, it starts to drop off. Geostrophic balance doesn't work on timescales shorter than a few days. You see about 3 days, it's dropping quite significantly. So that opens another question. Randy was talking about this curvature term. There's also the d by dt term, and we're measuring the current. So we could, in principle, add that in as well, the rate of change of flow. That will be interesting to see if you can extend this into higher frequencies. The other interesting thing is the current is responsible for most of this coherence at high frequencies, and still relatively important even at 100 days. But as you get to those lower frequencies, the density term becomes equally important, and it's only the combination of the two that's really working. Yep.
So the density term comes also at RS, the differences of with the first layer.
Yes. Yeah.
The upper layer to the bottom layer.
Yeah.
For example.
Yeah. It's the difference.
Okay.
It's a hydrostatic part of the pressure difference. And this is one thing that I dragged out all my data from 10 years ago, and I haven't looked at it since then. I remembered that we'd actually made some measurements off the coast of Spain at the same time, which we never got enough instruments back to do the full analysis that we wanted to, but we could do this mode 0. So I thought I'd have a look at that. And this is just the mode 0 from Scotia and the best estimate we can get from the few BPRs we got at Spain. And there's actually a correlation between those two over, we've got a 2.5 year time series there, 3 years, a correlation of 0.564. So there is significant coherence right across from the east to the west Atlantic in this mode 0. And I'm sure you could do a lot better than that. Right, so that's the data. Onto this broader context. This is a thing that I do like showing, and it takes far too long to explain, so I should stop. But it's a way of showing the variability and something about the spectrum of that variability at each point. So the brightness tells you how much variability in sea level we've got in this case. And the color is a measure of the spectral shape. So what you're seeing here, this is from satellite altimetry, and this one is from a model, 12th of a degree ocean model, capturing both really quite nicely, the amplitudes and the spectral shapes. And this is what Ken was talking about, is this insulating effect of the continental slope. This black line is low variability. There's a real sudden drop in the amplitudes. And then when it comes back up, it's a different spectrum entirely. These are decoupled kinds of variability. Not completely decoupled. Some of those large length scales do get across. But the vast majority of what you're seeing here in the open ocean is not getting across onto the continental slope, the continental shelf. But the main reason I wanted to show this is it proves that the model is actually pretty good. Because although we can do that at the surface from satellites, if you want to see what's going on in bottom pressure, we have to look at the model. So this is the model spectrum and sea level. We go to the bottom pressure. Totally different. This has been brightened up. I've multiplied everything by powers have been multiplied by a factor of 10 so that you can see things. And I'll just do a blow up of the North Atlantic to show some characteristics. That's a whole other story. Yeah, it's real. It's in the observations as well. Still a real minimum on the continental slope, both sides, even over on the west with all this mesoscale eddy energy. There's a huge drop in the amplitude as you go up the slope. You can see the mid-Atlantic ridge here having a big effect on very large length scales. And then this blotchy, colourful stuff, that is the mesoscale edges again. Some of that energy does reach down to the bottom, particularly where you've got a flat bottom in the abyssal plane.
Chris, sorry.
Yeah. So the colour is, you can think of it roughly as if your spectrum is a two-stick spectrum, so steeply sloping and then gently sloping, is the break point. Yeah. Yeah, so it's the frequency where it starts dropping on. That's it's more complicated than that, but that's a good interpretation for most purposes.
To the mesoscale edges where we do longer time scale.
Yes. Okay, so this minimum, what's going on along there? I always try to have this perverse thing about looking at places where nothing's happening. Because it's much more interesting than where lots is happening, because lots tends to be noisy, and nothing is clean signal.
So if you go one side back, that means that basically the west coast of the US, kind of the northwest coast, that's the best place to do the Odyssey because it's really boring for an hour.
Yeah, absolutely. So this is me extracting pressures along this boundary. So from I've just done the Atlantic in this case. That's the whole Atlantic, 0 to 6. The black lines are the equator. And this is mode 0 extracted along those points. And you see highly coherent, not super coherent. There are differences, and that's actually quite consistent with the data. So 2.55, that's Gaussian slope. This is where the Spanish coast is. And if we go to longer time scales, this is periods longer than 1.5 years, it gets even more coherent. So that's just the Atlantic. This is the entire world. And you really do have to split up into these different vertical modes to make any sense of this. So that's what I've done. I've done the mode 0 plus first and second DOF after you've taken out the mode 0. So, these distances between the numbers, they're 10,000 kilometers by some preferred measure, depending on wiggliness. But it's a good guess. And this is the linear trend in bottom pressure along the entire world over this, whatever it is, 25-year period. These are in millimeters per year. It's a non-linear scale, so most of the stuff, this orange to cyan, is less than a millimeter per year trend. There's lots going on in the Atlantic. That's the western boundary of the Atlantic. That's related to the overturning circulation. Outside the Atlantic, well, this is the whole East Atlantic. I mean, nothing, seriously nothing. And if you rebase it so that you're doing it relative to other places, you can make this look like seriously nothing as well. It's very, very quiet. Yeah.
So is what you're calling mode 0, is that going to be equivalent to sea level, or is there a density?
No, sea level is, so these modes are modes as a function of depth. Sea level would have the contribution from each of those modes at the top. So each one is, mode 0 is constant, independent of depth. The others are positive, then negative, and then reversing several times. So that's on really long time scales. So you go to shorter time scales, this is everything. And that's the 25 years again. You can see these things propagating away from the equator. So that's the East Atlantic. The propagation away from the equator. These are the continental shelf waves that Ken was talking about. They're going in the right direction. If you you have a blown up version of this, you can see them propagating towards the equator on the other side as well. So that's the correct way around. This is the whole Eastern Pacific, all the way around here. So
What are the phase speeds?
phase speeds are they're near the equator. They are Kelvin wave speeds practically. So 2.5, 3 meters a second. And as you get to higher latitudes, they go faster, significantly faster. They can be up to, well, I can't distinguish, but they get over 8 meters a second. So even quite quickly, you get this very high coherence over very large distances.
Just a stupid question. What's the data? Is it sea level? Is it
This is all bottom pressure from the model.
from the model?
Yes. Yeah, so that's what I hope to say. Oh, not too bad. We can separate the dynamic from the total pressure by using this stepping method, as long as we are interested in pressure differences. So you can't get the absolutes by this method, only the differences. But those differences down the slope, I think we can do really nicely with the right combination of instruments. The observations do show long distance coherence, even between eastern and western boundaries, but we really don't have the observations to test this very, very well yet. So that's why I think all of this is exciting. We're starting to get those. And the models say, actually what we're seeing so far is just a hint of the enormous coherence that should be out there if you believe the model. The model does well at the things we know we can test, which is measurements at the surface. I'm assuming it does well at the bottom as well, but who knows? So that's a big thing to be tested. I think it's really exciting stuff because that tells us about really global scale oceanography and the interconnections between the ocean basins. Okay, that's all I had to say.